All right, so where we left off with is, like I said, you guys read an article comparing 4 of the main greenhouse gases: carbon dioxide, water, methane, and nitrous oxide. Your article used carbon dioxide as the benchmark. And then from there, we compared lifetime in the atmosphere, source, contribution to greenhouse effect, and warming potential. We looked at those features. And that was Friday. And then you guys with the sub started writing a greenhouse gas CER, where you argued which greenhouse gas we should be the most concerned about. And you could have, by the way, taken on a different perspective as long as you could argue it based off of data. Automatically, just a little note before you submit or ask me to grade your CER. A lot of you guys I was scanning, are writing decent CERs with data, and that's awesome. But you're forgetting that if I'm asking you which is the most dangerous, I assume you're going to make a comparison, which means I assume you're going to talk about other greenhouse gases and why we shouldn't be as concerned about them. So if your CER only talks about one gas and you never mention another gas, you are not making a comparison, you're making a summary sheet. Okay? So you're making a compelling summary sheet. So make sure that you still mention why the other gases aren't as much of a concern. You don't have to go into great detail, but you should at least address and acknowledge, okay? Because I asked you for a superlative, right? What's the most out of the rest, all right? So make sure that you address that. But that's where we left off, where you write your CER. And now we're gonna get into the next kind of principle in answering our unit question. Will we lose our Santa Barbara beaches? In order to understand that, we are going through multiple principles that kind of give us the big picture on how things work together to explain the phenomenon of global warming. We started off with greenhouse gases and comparing greenhouse gases, and now we're heading into what we call feedback loops. This idea of, well, how do the greenhouse gases affect, build off of one another? Okay. So feedback loops. How do changes to Earth's climate affect other systems? Please make sure you have your notes out right now. What we have here is we need a little reminder as we talk about feedback loops, the second principle in understanding everything. We need to remind ourselves what a system is. And a system is a set of components or parts that work together. So we are a system, right? Our classroom is a system. And of course, the boundaries by which you define a system affect. I could say a system is just me and Eliana working together. I could say a system is these 2 rows. I could say a system is our entire class. I could say a system is the entire school. I could say a system is the entire education. Where you put the boundaries matters. But either way, a system is whatever I include in that system, I assume is working together in some form or fashion to contribute to achieving a task or a goal. Okay. Input is whatever we put into the system. Kind of pretty much the components, unless your components are energy. It's a little hard to name energy always, like as something that you can like physically see. So sometimes you get more abstract components coming into it, but nevertheless, and then the output is the whatever is the result, whatever is the consequence, whether chosen or unchosen, right? You can have non-desired consequences happen where you're like, oh, that was not part of the plan, but that's still an output. Okay. So by feedback, when we talk about feedback loops, then when we say by feedback, we mean the response of a system as it feeds back into the input to the same system. So instead of being linear, which is what we think about often, I have an input, I have an output, and it's done. That's a very linear system. That is it starts and it ends system. But when we think about feedback loops, we think about, okay, whatever ends up actually becoming the new input. The end becomes the new input. So it kind of spirals on itself, right? This isn't too hard to think about. It's just hard to explain when I ask you to explain it in terms of greenhouse gases. So you want to make sure you're confident in what it means. Okay. Not here. So in the context of climate, we can visualize the atmosphere or the ocean or the earth in general as a system with a number of inputs: water, energy, carbon, etc. Right? Man-made sources, human like erosion and damage, human impact that is good, cleaning up the beaches, right? There's a lot of inputs. A given input changes the system and causes a response or an output. that also impacts those same inputs to the system. The feedback is not necessarily immediate and can require several steps or involve several components, but it eventually returns to the same starting input. This process of system output affecting the input is called a feedback loop. So what you'll notice is when we talk about feedback loops, we're going to isolate to one feedback loop at a time. But oftentimes what you'll actually see is that feedback loops have feedback loops coming in on each other. So you can kind of think of it like a spider. One feedback loop will feed into here, and that will feed into here, and that will feed into here. And what you get is a round of cyclical feedback loops that all attach to one another through one specific component. Which, by the way, is actually the case with environmental concerns, is we can't look at just one feedback loop and say, if I just fix these things in this loop, I'm good. Feedback loops are very integrative, and that's what makes it so complex to solve the issues that we see, is that you're really, when you're trying to address one feedback loop, you're really addressing thousands of feedback loop on one another. But we'll isolate it for right now to just one feedback loop to understand. So for just some context to kind of see feedback loops clearly, it's can be a little bit more confusing with environmental. Let's look at a biochemical feedback loop. So what we have here is when we look at your internal homeostasis and your body's systems and mechanisms to keep yourself at a reasonable temperature, right? What we see is that we have an example of a feedback loop. So let's say that you get really hot, okay? And what we say is that the temperature rises, okay? So what you do is you have a rise in temperature, okay? What happens is that initial input, okay, will create, and I'm actually gonna move that here to a rise in temperature. That initial input will create a response. And that response, all right, will trigger your sensors or your neurotransmitters, okay? When your neurotransmitters respond, what happens is that you see that the brain, and you know what? I actually think I like this here, sensor. When your sensors, okay, send messages, it sends messages to what you call your brain control or your brain hubbub, okay? And that part of your brain begins to process that information, triggered, okay, from the rise in temp, carried by the sensors. And then as a result, what you see is a response through sweat glands. It activates your sweat glands. Okay. And as you activate your sweat glands, what you're really doing then is you're losing, okay, heat to then get your body back to its ideal temperature of about 37 degrees Celsius internally. But your body never stays there because the environment's always changing. So we call it a feedback loop because you're always seeing as you lose heat, then you become too cold. And then you have other factors. You're never really one and done. Like you don't do this cycle once and you're good for the rest of your lifetime. Okay. It's a constant adjustment. And what we would say then is that this is an example of what we call a negative feedback loop. Because what we see here is that the trigger is opposed by the response. You can almost call it an inverse relationship within a feedback loop. A positive feedback loop would be if you were hot, rise in temperature, your brain senses it, the output, the response is it activates sweat glands, and that made you hotter instead. You actually increase your temperature. Okay, that would be an example of a positive feedback loop. That would kill you. Okay, so a lot of our homeostasis is negative feedback loop examples. But that's kind of your biochem example. Let's move on to now climate, how we transfer this to the climate. So changes in Earth's climate is full of examples of feedback loops. Like I said, most of the issues that we are facing in our climate are super complicated to solve because they're hundreds and thousands of feedback loops intertwined together. Okay. These feedback can reinforce each other and take the system in a given direction. For example, warming the planet will decrease the amount of ice and snow at the poles, which will decrease how much light is reflecting off of the Earth, which causes more absorption and therefore more warming. So we see that as an actual, what we call a positive feedback loop, because as we see the Earth warm, its output, its impact causes a result that makes the Earth warm even more. That's why people are so concerned about warming. Is you're like, oh, if we're rising in a steady temp of like 0.2 degrees Celsius over 20 years, that's not a big deal. But it's not a steady response, according to what we're seeing. Is we're actually seeing every time we get warmer, we exponentially essentially get warmer because we build on getting warmer. It's not steady. It's not linear at all. It spirals up. And it builds. And that's what's so concerning and why we see such a big push for immediate action. Because time, if all the data is being interpreted correctly, time is not on our side with these. Now, we do see small instances when warming can lead to cooling. That would be called a negative feedback loop. Very small instances that helps control the climate system and maintain a more constant temperature. These are the type of feedback loops we want to emphasize as far as environmental chemists. We want to look into what we can do to create, emphasize more of these negative feedback loops, that as the Earth warms, we actually produce a cooling effect. For example, increased evaporation due to the warming environment, and cloud formation increases light reflection from clouds, which causes less absorption and less warming. Climate modelers test these positive and negative feedback loops in their computer systems to determine if the net effect of all the different feedback loops will be overall positive or negative. So let's complete the feedback loop below, and you guys are going to have to do this on your test. You're going to have to take some data and explain what it's demonstrating in a feedback loop. Okay. So let's say here we have this initial phenomenon, global temperatures increase. What happens then is what we see is evaporation. Out of these options, evaporation will increase. Okay. And then what that means is that the water vapor increases. That's the change or and as a result of that kind of successive series chain response, we see the final response, quote unquote, being that eventually greenhouse effect is enhanced. And if your greenhouse effect is enhanced, your global temperatures continue to increase. And if your global temperatures continue to increase, you're going to get more evaporation. You're going to get more water vapor, and you're going to get more greenhouse. And so you see a cumulative effect beginning to build. This, of course, is an example of positive or negative feedback. Positive, because as I get warmer, I result in an effect that also contributes to it continue to getting warmer. So how does this work with explaining melting ice, which, by the way, is integral to understanding whether sea levels rise? So our kind of third phenomenon, or is the fourth investigation in overall. No. What we see is we're going to watch a couple simulation videos. And what I want you guys to do is, while I get these videos loaded, start thinking about what might be as you look toward finishing this little thing up, what might be the feedback loop that we will be seeing with melting ice, and make a prediction about whether land or sea ice causes greater increase in sea level rise. So while I switch over to video, go ahead and do that. Okay. All right, so hopefully, guys, you made your prediction on page 6 in your notes. Which type of melting land or sea ice do you think will cause greater increase in sea level? Out of curiosity, who said land ice? How many people said land ice? Could you just raise your hand? Would cause greater increase in sea level? Okay, who said sea ice would cause greater increase in sea level? Okay, interesting. All right. So whatever you chose, totally your prerogative. And let's go ahead and look at this phenomena of melting ice that brings us back to the idea of how do feedback loops particularly connect with our issue of sea level rise. So here is your first video. And in your notes, you're gonna wanna take note in the table on page 7 about the changes. Drea, I don't know how you're watching this when there's no words and you're not looking at the screen. Okay, so in your notes, you should make a mental note that on page 7, you have a little demo of their setup in drawing. So before melting, what do you notice in both of these scenarios? Quickly just write down what you notice about the level. And you could, by the way, totally do this type of stuff at home with your like niece or nephews or little siblings. I do try to include some fun activities, like I know via video mainly, but that you guys can do at home when you babysit people. I think it's cool to get kids into science. Probably like some type of clay or putty, my guess is. Okay, so there's your little note. Now let's continue on. Okay, now what do you notice after melting? What happened? What changed? And everyone's like, what? All right, so which one actually demonstrated greater sea level rise with the melting? Land or sea ice? Land ice. Land ice melting created greater shifts in sea level. All the little people. Maybe there should be them trays. All right. So don't soil absorb water? Yeah, but what we see is like rivers, right? You all that water flows down eventually. Like soil can only absorb at such a fast rate. So we don't see necessarily as thorough of absorption that you might be thinking of. All right, so let's quickly look at your notes. I'm gonna stop screen share here and switch on over to notes. So what we saw then is for our little demo, before melting, okay, pretty much what we see is that we have a lower level of water. And before melting, we had a higher level of water. But after melting, we see that the the sea level increased, but here it remained relatively constant. Okay. And so, I'll go full screen, sorry. Okay. So, in which situation did the water rise more? Well, the land. Now, why does this make sense? Because land water isn't included in the volume of the water already. Land water melting, or land ice, I guess you could say, sorry. Land ice melting, okay, is an addition. It's an addition to your seas / oceans. But frozen water in water, it's still water. So frozen water doesn't really have that big of a difference in volume. In fact, frozen water expands. It's more spacious, ironically, in terms of particle, which is what's so unique about water, is that when it freezes, it's actually less dense, which is why ice floats. So that's kind of what we see. So then how does this relate to ice melting on planet Earth? Well, what ice on Earth is land versus sea ice? And what are some of the other effects that ice melting might have besides sea level rise? Now let's head to the second video. Okay, why do we care about adding more water? Okay, we got hinted at in the last video, oh, it's going to cause a little bit of extra flooding. Okay, we can survive. Florida survived for, eons with flooding. They all still decide to live by the bayou, right? So why does this really matter, and how does it directly connect to the amount of ice on Earth? So now I'm going to switch back to my other video screen share, Gee Willikers. And let's move this down. All right. And we might be having an infomercial.
You've likely heard about the effects that climate change is having on our planet, and specifically in the Arctic, which is warming twice as fast. But what would actually happen if all the ice melted on Earth?
I can help with that. When you and I drink water, we drink non-salty water, fresh water. Now, of all the water in the world, most of it is salty. Just 3% is not salty. Now, of that 3%, you can't get to most of that because 70% of that 3% is frozen. 30 million cubic kilometers of frozen water. And it's so much frozen water, so much ice, that if you had a layer of 1,000 meters thick, it would cover North America. That's a lot of frozen water, people.
On land, frozen water forms glaciers, ice sheets, permafrost, and snow, but the Arctic is largely ocean, so there it takes the form of floating sea ice like icebergs. And because it's in direct contact with warming waters, sea ice will be the first to melt as global temperatures rise. In fact, this year, NASA reported that the extent of Arctic sea ice was the lowest ever recorded for January, February, April, May, and June 2016.
So the world is getting warmer and the ice is melting. Pretty soon you'll be able to drive your ship from Europe to Russia, right over the North Pole with no ice in the way. That's good for certain shipping companies, maybe, but for the marine species, the polar bears, the walruses, the seals, they don't have their old habitats. They're all going away. They're melting out from under them.
And ocean-dwelling animals like bowhead whales and narwhals aren't immune to these changes either. As sea ice melts, energy and oil companies are taking it as an opportunity to search further north for untapped resources. Using a process known as seismic blasting, they shoot air explosions into the water in an effort to map the ocean floor and find oil. Of course, this has detrimental effects on the whole ecosystem of the Arctic Ocean, while also causing physical trauma and habitat relocation in whales. In terms of sea levels, melting sea ice won't have much of an effect. This is because the floating ice already displaces roughly the same amount of water as it would produce when it melts, so the net effect would be negligible. Furthermore, the majority of Earth's ice, more than 95%, is land-based and contained mostly in enormous ice sheets that cover Greenland and Antarctica, where there are entire mountain ranges almost as big as the Alps completely buried in ice. So what if all the ice on land melts?
If all this ice melts, the ocean's going to have more water in it. So the sea levels, as measured from the coasts, is going to go up. It's going to go up 70 meters. That's a long way, people. Half the world's citizens live on sea coasts. That's where the commerce action is. So they're going to have to move. Where are they going to go? And who's going to pay for it?
Tokyo, New York, Sao Paulo, Mumbai, Shanghai, and Jakarta are all coastal and happen to be some of the world's biggest cities. Even a small sea level rise of only a couple feet could cause up to $1 trillion worth of flood damage per year. A rise of 10 meters would displace more than 630 million people, nearly 10% of the world's population. At 25 meters, 1.4 billion people, roughly 20% of humanity, is left homeless. And to visualize the full 70 meters, the rising seas would drown out most of the US eastern seaboard, much of the west coast, the entire state of Florida, huge areas of Asia, including Bangladesh, and much of northern China, and create a new inland sea in Australia.
At the north and south pole of the Earth, we have a lot of ice. Ice is white. Ice reflects sunlight into space. But there's a feedback mechanism, one thing leading to another. As the world gets warmer, the ice melts. As the ice melts, it's reflecting less sunlight into space, which lets the world get warmer still. The sunlight is absorbed by the dark, liquid ocean. So as the ice melts, the world gets warmer, and the sea gets fresher.
Currently, the world's oceans are crisscrossed by a set of currents that act like a giant conveyor belt.
That phenomenon is, by the way, called albedo effect. We're going to study that at the end. That's our last kind of subtopic in this unit that we will study, is this whole idea of reflective material.
And these currents are powered in part by the differences in the saltiness between one part of the ocean and another. So if a melting ice sheet in Greenland dumps a whole bunch of non-salty fresh water into the North Atlantic, it's possible that it could disrupt the currents.
So the conveyor belt takes chemicals, takes nutrients around the world, which feed plankton, which feed fish, which feed us. Half of the oxygen you breathe is made by plants in the ocean, so you don't want to mess with this. Furthermore, as that sea surface gets warmer off of Greenland, the Gulf Stream will probably shift a little bit. And if that shifts, what keeps Europe warm right now may not keep Europe as warm. So the crops are going to have to be grown elsewhere. And who's going to grow them? And who's going to ship them around? And who's going to feed each other? And what's going on? This is serious business when you go melting the ice.
We actually went up to the Arctic to see the current state of things firsthand while documenting it all, and were absolutely shocked by what we found. Click here to watch our documentary, The End of the Arctic, where we learn.
And that is where the information begins, or information ends, and the promoting begins. So if you look at your notes, what we see is, and I'm going to switch on over to my notes again. What we see is a couple questions that we need to answer based off that video. So is the Arctic mostly land or sea ice? Sea ice. So does it necessarily contribute to, other than the environmental habitats for animals, does it contribute to sea level rise? Not really. So what's our actual main concern then? Yeah, the land ice in like Greenland and Antarctica. So what we see here is Greenland and Antarctica are land ice, and most of the ice actually on Earth is land ice. Okay, so what are some of the effects of melting ice from videos from the video? Well, of course, the environmental aspects, the awful decisions that companies make and industries make to implode like underwater bombs, essentially. I don't know who thought that was a good idea. I actually saw this really interesting Instagram reel of a person who threw a pound of pure sodium metal into a river. Yeah, which looks really cool, except for the fact that remember it releases toxic hydrogen gas. You also just see a massive amount of energy release in that little localized area where that metal was. What happened to the creatures below? Like, that's what's kind of crazy, is that I don't really understand, wherever you fall on the spectrum of like environmental politics, I think we can all agree that everything you do as a human impacts something in this world. Like your very existence impacts like this world. It's why we value life so much. But when we have like major companies like being like, yes, let us bomb the underworld, like what interesting decisions. But nevertheless, there's been a lot of good done in the name of science that required a lot of sacrifice in the process. So I don't know. But I think the biggest interesting thing that I took note of was that there was an potential for the increase of 70 meters of water on the coast if all the land ice were to melt. 70 meters. Okay. I think it's like what is it? Like 2-ish feet is a meter. Okay. 2.5-ish feet is a meter or something like that. Not great. Not great. But yeah. So then what we see is not only when we consider the feedback mechanism of ice melting, and he started touching on that at the end. When ice melts, you also have less things that reflect light. So you're also getting more absorption of the energy and stuff like that. So another kind of side feedback loop that goes into this phenomena of ice melting and therefore sea level rising is this idea of thermal expansion. Now, I mentioned that water is actually, when frozen, less dense. But what we see is not only are we seeing sea level rise increase from just a pure addition of volume, but we're also seeing a characteristic in the molecules themselves creating expansion. This is known as thermal expansion. So what we're going to see is, again, a really short video. And let me stop screen share. And what I want you guys to do is, as I play these two videos, you're going to take notes on these two videos, and then that will be the end of class. So quickly, while I'm getting this video set up, please read the questions that you're supposed to answer. You're going to watch a video on liquids, read the questions, the 3 questions, and then you're going to watch a video on solid expansion, read the questions while I get the video set up. So we're going to hit the liquids thermal expansion. Hopefully the video will clear. What we have here is 4 different graduated cylinders that I've been put a stopper in it. Sorry, it should clear up in a second quality wise, but your 4 graduated cylinders in your notes is supposed to be labeled. So the first one is salt. The second one is methanol, a type of alcohol. The third one is, I'm trying to read it. Something, I can barely read that third one, but the last one's oil. I think the third one is just like plain water. So let me see if I can get this to get better quality. Hold on. So what you should be seeing in the video is that these liquids are being heated up. Let me try. Man, deionized water. The third one's just water with food dye in it. And sorry for the poor quality of video, but we're just basically watching what happens as it heats. It's not the most exciting video, I admit. And I love how they never put music. They should have put music with this. Okay, so I think it will be best in a second once I pause this video to show you the end versus the final, because it's pretty hard to see right now. Ah, there we go. Okay. Here we go. So this is the end result right here. Look at your values. You're at about 60, a little less than 60 for oil, a little over 60 for water, on your way to 65 for alcohol, and just a little bit over 60 for salt. Okay, that's where you ended. Look at where you began. Gee willikers. What the heckaroonies? Well, what you should see, this is the worst, is you're all at 50. You're all at basically 52, 53 in the beginning. Okay. So what we Sorry, this video did not work. It worked last time. I don't know what's up with the Wi-Fi. What if let's see, optimize for screen. Let's do that. Maybe that will fix it. And let me see if I reload the page, if it would fix it. Because I'd like you guys to see the change after a Grammarly commercial. Or a suitcase commercial. Please load. Well, I'm about to give up. Hello? Okay, I'm giving up. I can't do this. I'm not patient enough. So, okay, how to make it stop? We'll just deal with you later. Please stop. Please. Oh. Okay. So anyway, what you're supposed to see is that the water levels rise, and it rises actually the most in the ethanol in the water. The ethanol and the water have the most increase in liquid with just simply heating. Notice there was no addition. There's no addition of liquid actually to, please stop playing. There is no addition of liquid actually to the graduated cylinders, but you saw that the liquids expanded nonetheless. The molecules, as they heat up, as we know, move faster. When they move faster, they collide more. Okay, as they move faster, naturally, if you're colliding, you're going to naturally kind of create distance in space because you're going to take up more area. You're going to push out on your environment. And if your environment's rigid, what you're going to see is you're going to go up. Okay, so that's kind of the big idea. And then with solids, the same thing is true with solids. Yeah. What you'll see here is that this is kind of like the ball and ring example. We see here that even with solids, we see the similar phenomenon. We see that if we heat up a solid, we see expansion in the molecules, despite there not being an actual addition of more molecules or more.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius, and even dead.
There you go. I don't know what other video is playing right now. And now it no longer fits. Pretty simple demo. But these simple demos give us an idea of a very complex issue that none of us seem to be able to solve. Partly because it involves like everyone getting on board, right? But try stopping all of the solids and liquids in the earth from expanding with increase in temperature. That's quite the feat. Very simple concept, incredibly difficult to address. Okay, so what you're gonna wanna do, and we're gonna talk about this tomorrow as your warm-up, is your notes are gonna be pretty minimal. You could even just write one sentence observation about what you should have gotten out of each, the liquid and the solid example of thermal expansion. But what I really want you guys to focus on is questions 4, 5, and the summary. That's what you're gonna share tomorrow morning for your warm-up. And it's going to be starting to be a good practice for your upcoming test is, can you take some of these theories and start putting them into cohesive explanations of why we see certain things? Can you take these principles and apply them to the context of, hey, how does this impact this? Why am I seeing this? And why is this so difficult to address? Okay, so please fill out questions 4, 5, and 6 in your notes on page 8. The videos are also hyperlinked on the notes if you actually want to get a better video of them, because hopefully your Wi-Fi is faster and your screen does not pause a ton and glitch. And that is the end of today. And tomorrow we'll address our last topic, which is albedo effect, which was hinted at by Bill Nye. So good job, you guys.